In this video, we're going to talk about the acetoacetic acid ester synthesis, which is a whole mouthful of stuff, but we'll see what it is in a second. Well, we're going to start off with something simpler. Here's a simple enolate, and we're going to treat this with ethoxide. Here's a simple ester. We're going to treat it with ethoxide to get an enolate. So what proton is going to be pulled off? You all know the answer to this. Which one of these down here is an enolate? Well, there's only one that's an enolate. It's E. So the ethoxide is going to pull the proton off over there, comes and grabs it, forms our enolate. Now, if this was all there was to it, this would be kind of boring. But the interesting thing about this is that enolates will react with esters. And if we just made our first enolate, we have a whole lot of ester left. And so what can that do? Well, we can do the reaction where you form an enolate and then it reacts with another mole of the ester. So draw out that enolate. I'm going to let's stop the video here a little bit. Draw out that enolate and allow it to attack a second molecule of the ester. See if you can figure that out. Pause the video. Okay, did you do that? Well, again, I know you didn't, but let's pretend you did. Okay, so what's happening? There's the enolate. And of course, here's a second resonance form of the enolate, and so this carbon is going to act as essentially as the nucleophile, and it's going to come attack another mole of the original ester. So it's come around, grab that carbon of the carbonyl, push the electrons up there. We got a conventional 4-coordinate intermediate, and of course, what we're going to do is we're going to kick out the best leaving group, which of course in this case is going to be ethoxide. And so we kick out an ethoxide, and what do we make? Well, we make ethyl acetoacetate, or acetoacetic acid ethyl ester. Okay, so we've made the compound, which we're going to use as a starting material for various syntheses. So how does this going to work? Now, this particular reaction is called the Claisen condensation, and it's in chapter 26, and don't worry about it a lot. It's actually very simple, but we'll talk about it later. But for now, we're going to use the molecule we just made to do a synthesis. So here it is, acetoacetic acid ester synthesis. Okay, so this guy is quite acidic, of course, because we got two carbonyls beta to each other. So this is a beta keto ester, as they call it. It's beta because there's two carbons around, a keto because it's a ketone, and of course it's an ester. So this beta keto ester is quite acidic. That proton can form an anion delocalized over both carbonyls. So we're going to pull off that very easily. Now the base you want to use is ethoxide because it's an ethyl ester. If you use a different base up here, you can end up reacting with the ester. In this case, sometimes that ethoxide is going to come in and attack the carbonyl. But what's it going to do? Well, it's going to kick out an ethoxide. So it's a net nothing reaction. If you use methoxide, you would end up, switching in making some methyl ester, and that would just kind of screw things up. So you always want to pick the anion corresponding to the ester that you're using. So we're going to pull that proton off. We're going to form this nice delocalized anion. These things are pretty stable because it's delocalized over both carbonyls. And here we can actually draw 3 good resonance structures. Here I'm drawing the one with it's on the carbon, but of course there's the third one with it's on the other carbonyl. Anyway, this carbon center can be alkylated. Or another way of saying it is this is a pretty good nucleophile. So if this is a good carbon-based nucleophile, and it'll do SN2 chemistry. So all we need to do is to give it a nice here an alkyl bromide to react with, and we're going to simply come down, do SN2 chemistry, come in on the backside, kick out the bromide, and we've alkylated this guy. Now that's kind of fun, but let's do some more chemistry. Let's throw in some base and hydrolyze the ester, and then we can reprotonate, and we got our carboxylic acid. But what's going to happen? Well, what video did you just watch a few minutes ago? Decarboxylation. Look at this. You heat that up, that CO2 is out of here. You can draw the mechanism. In fact, you've already drawn the mechanism today. Of course, you just switch this up. The hydrogen's up here, bridging over to the CO2, and draw a nice little cyclic thing of 3 arrows, and you've done the decarboxylation. So look at the net result here. We've done this alkylation on this guy up here, but then we lose the CO2. This is essentially the equivalent of alkylating acetone, because see, we've added these 4 carbons over here. This carbon and this carbon were in the original molecule. So that's the same as taking acetone and alkylating it. So that's kind of neat. Oh, here's the decarboxylation written up here. Okay, so decarboxylation will occur whenever you have a carboxyl group which can form an enol beta to the carboxylic acid group, and which is this will happen here. Okay, so let's go back and look at this just a little bit more. This is when you look at this equivalent way of doing this would be to take our good old friend acetone, you throw in some LDA, you form this nice lithium enolate, and you could alkylate that to get to the same place. So this, what's in the box here, is essentially equivalent to what's in the box here. So the acetoacetic acid ester synthesis is essentially equivalent to an LDA acetone synthesis. Now, what's the difference? Well, one is the conditions are much milder here. In this case down here, all we used was ethoxide, and you can basically do this. This is basically compatible with you know, very mild conditions, and you can have water. You know, water is not going to kill this reaction. This is a pretty simple reaction. This LDA, of course, your non-aqueous solvents in lithium, the lithium diisopropyl amide, you have to form very carefully and much more attention to detail. And the important thing for the purpose of this course is this much milder chemistry is going to be a direct analog to various biological processes, which we're going to talk about later. So these are essentially, you consider them synthetic equivalents, but one is much easier to do than the other. Okay, so what else can we do? Well, let's just do another example. See if you can figure out this. This is again one of the quizzes down below. See if you can figure out this product. Again, try to pause the video. Try to work it out before going on ahead. Because all what we're going to do, of course, here is we're going to form the anion. We're going to do our alkylation, and then decarboxylate. So can you draw that down? Okay, we'll restart. Which of these products are you going to get? You drew it out. You should be able to recognize the product. You know, they all look pretty bizarre. You know, which one it corresponds to alkylating over here. All right. Well, we're going to have we can count our carbons. We're going to have that methylene and a phenyl. We're going to have the 3 carbons here. So we're going to have the benzyl group is going to attach right there. So what we're looking for is a methyl, a carbonyl, 2 methylenes, and then a phenyl. So where is that compound? It's good old friend C over here. So how does this work? There's our enolate. Here's our R group coming in. Do your decarboxylation. In this particular case, R is benzyl, so that's molecule C. Very good. You figured that out. Okay. We could stop there. You don't have to do the decarboxylation. And the importance of stopping here, of course, is that we can do further reactions on this molecule. So let's do another reaction on this molecule. We can still form an enolate, right? It still's got a proton there. So we can throw in another mole base, form a new enolate, and we can alkylate again. And so if you do this, you put on a second alkyl group. So what's this one going to give? Well, again, we're going to put an ethyl group right there, and we're going to lose the CO2. So we have to have our benzyl group. So all these have some phenyl in them, but which one's got the benzyl group in it? Well, the benzyl group is 1 carbon away, so it's A. And of course, here's our benzyl group. But wait a minute, the ethyl's on the wrong side. It can't be A. C also has that group in it, but now we've added the ethyl group down here. So this is going to be C. Okay, and so when we're done with that, and we've got molecule C, and of course we can decarboxylate that. When we decarboxylate it, we actually get molecule D. All right. So this sequence goes from first you first make C, and then when you do the decarboxylation, you make D. Okay. So again, that's pretty slick. So ethyl acetoacetate is a good general method for making substituted acetones, because what you do, you add base, you form an enolate, you alkylate, you can decarboxylate. So you got 1 R group on an acetone. Or you can add another molar base, form a new enolate, alkylate again, and that would give you the equivalent of 2 R groups on an acetone, on the same carbon, by the way. So it's a general way of making substituted acetones, well, when they're substituted on one side. And so this is a good synthesis, and you should be able to do these problems without any difficulty. So here's a very closely related one. This is diethyl malonate. So the simple dicarboxylic acid is called malonic acid. So this is diethyl malonate. Well, diethyl malonate works very similar. You add base, you form an enolate. You can alkylate, and you can decarboxylate. In this case, what you do when you hydrolyze the OH, of course, what you're doing is hydrolyzing esters on both sides. To decarboxylate, you'll lose one of them, but the other one will stay behind. And this is simply a carboxylic acid. And it's a substituted acetic acid. You've added that R group to the methyl of acetic acid, the equivalent of. So that's good. But again, you can do the same thing. You can add another molar base, and you can alkylate the second time. And this, when you decarboxylate, gives you a disubstituted acetic acid. So malonic acid, the malonic acid synthesis is a general method of making substituted acetic acids. So we can kind of put these together. The acetoacetic acid ester synthesis, the word acid is missing, is a general method for making substituted acetones. You alkylate once or twice. The malonic acid synthesis is a general method for making substituted acetic acids. You alkylate once or twice. So these are kind of fun reactions, and the problems below will give you some chances to practice.